Welcome to the lecture on weldability of carbon steels. So, we had the introduction about the weldability, and that is very important to have a good weldability, because ultimately the welded specimen which you are going to use, they are supposed to perform satisfactorily under the specific set of conditions. So, we talked about the definition of weldability, how the weldability may be affected because of the constituent elements. Then what are the tests which are done for checking the weldability. So, we will be talking about the weldability and issues related to that in different materials. Typically, we will talk about steels, then we talk about the cast iron, and also few of the non-ferrous materials also, because they are the ones which are normally used for engineering applications, and we must be having proper information about the weldability aspects of these materials. So, as you know that we have nowadays use of carbon steel is there. Carbon steel is certainly when we are limiting the carbon to maybe close to 1% or so. But then apart from steel, like carbon steel, you have other like low alloy steels, then you have alloy steels, then you have another alloy of iron, that is cast iron is there, and then we will talk about the different materials. But in this lecture we are going to have the discussion about the material, that is carbon steels. So, as we know that when we talk about steel or carbon steel, then your classification is normally in that low carbon steel, mild steel, medium carbon steel, or high carbon steel. So, as you see that you have carbon content is given a range for all these kind of steels. So, in the case of low carbon steel, the carbon content is limited to a maximum of 0.15%, and its use is normally sheet, strip, welding, electrodes. All these are made by 0.15%, less than that even the carbon. So, that is classified as low carbon steel. Now, these have good weldable behavior, and as you know that once you are making the sheets or strip or welding electrodes, so for that it must have very good ductility. So, lower value of carbon ensures that you have very good ductility. So, they can be converted into sheets or strips or so, or even fine rods like for making the welding electrodes. So, they have a very good reasonable they are weldable. So, they can be welded, and normally if we talk about the hardness, then hardness is certainly smaller than as we go in increasing the carbon percentage. So, the hardness will increase. Then you have mild steel. Mild steel has carbon content of 0.15 to 0.3%, and it is normally used for structural shapes, plates and bars. And in this case the welding rating that is considered is from good to excellent. So, in fact the welding weldability may be considered to be even better than the low carbon steel. So, we will discuss that for which conditions or for what reasons the weldability is even better, it is said to be. Then we have the medium carbon steel. So, in this case the carbon is in the range of 0.3 to 0.5%, and they are normally used for the machine parts and tools. And here the welding rating is said to be fair. So, normally you have the preheating also requirement, or you have the requirement of post weld heat treatment. So, that is why it is known as the fair, and normally we will talk about it, that we normally try to have the adoption of low hydrogen processes to avoid the cracking or the any problem in the weld metal or HHR zones. Then if you come to the high carbon steels, so high carbon steels are basically classified as those steels where the carbon percentage is from 0.5 to 1%. As you see that their use is normally in springs, jigs, dies and rails. So, that you require more hardness. So, you have these high carbon steel. Now, in these cases the weldability is poor because of the very high carbon that we will see. As you know that with increase in carbon, the hardenability will be increasing, and if the hardenability is increasing, it means even at smaller cooling rates also you are likely to have the undesirable phases like hard phase and brittle phases like martensite. So, basically that way its welding is weldability is said to be poor, and you have to have the precautions, like you have to have the preheating as well as the post heating techniques that is required for avoiding any kind of defects or cracks, especially in the weld metal and HHR zones. So, coming to the welding of low carbon steel. So, as you know that you have the low carbon steel where the carbon steel is smaller. So, you have carbon steel is up to 0.13%. Now, in this case they are good welding steels, but not best for high speed welding. This is because the presence of very low amount of carbon and also manganese. So, if it is very low, in that case it is reported that they produce porosity in the weld. So, that way you have to see that you go for slow speed. So, that way you can avoid these formation of porosity, especially when you have low carbon and also you have low manganese. So, so that condition can be corrected by modifying the welding procedure. So, the procedure is means you must go low, speed should be low, so that your welding is okay. You are avoiding these formation of porosities in those cases. And basically if you have the product in such a manner that you don't you are not very much concerned with the presence of the internal porosities too much, in those cases certainly you can go with standard high welding processes, and that way you can have the economical process. So, so so that is the advantage. So, advantage of these steels, as we know that they have very good ductility and they are easier to form as compared to the higher carbon steels. So, so that is the otherwise there is not much of problem, because as the carbon is less, so ductility will be higher. So, apart from the problem related to internal porosity, there is not much of the challenge in these cases. Coming to the mild steel. So, mild steel basically where you have the carbon which is a little bit more maybe 0.15 to 0.2% or or 0.25% or so. So, they have very good weldability. So, in this case, so what we have seen earlier, we have the this is your mild steel. So, it is used for structural shapes, plates and bars, and they have good welding rating. So, basically they have very excellent weldability, and they can be welded with all types of mild steel electrodes. So, that is the advantage of these electrodes, and since the carbon percentage is somewhat higher, maybe you are going from 0.15 to 0.20, 0.25%. So, so if you have since in this range or 0.25 to 0.3% carbon, and when we have 1.4% manganese, in that case particularly they have excellent weldability. So, but the thing is that you will have to see control on the limit of these alloying elements, one or more alloying elements. If they are more than the limit, in those cases underbead cracking may be possible, typically in the case of fillet welds. So, you have to, in those cases you will have to have the control on the welding speed, somewhat lower the welding speed, and then you can have the satisfactory results. Otherwise, they are used for maximum production speed on assemblies or structures that require extensive welding. So, mostly most of the extensively this material is used for welding applications, and in those cases for maximum production speed you are going to use these mild carbon steels, because they show very good weldability. So, now one more thing which is defined in this case. So, susceptibility to this underbead cracking. So, that is increases when the carbon equivalent, that is exceeding 0.4. So, basically what happens that depending upon the alloying elements, whether it is going to have the effect on the carbon equivalent or not, I mean positively or negatively. So, as we know that carbon equivalent basically is defined, and carbon equivalent will be defined by the percentage carbon plus percentage manganese by 4 plus percentage silicon by 4. So, that way you find the carbon equivalent when we are welding such carbon steels. And what is seen that when this carbon equivalent value will be exceeding 0.4, in those cases the susceptibility to underbead cracking from hydrogen is basically increases. So, that is one thing which is basically seen, which is observed in the case of these mild steels. So, basically if you look at the composition and underbead hardness. So, a graph will be there. So, suppose you have the carbon equivalent on the abscissa, and suppose this is your 0.3, then you have 0.4, you have 0.5 or and 0.6, and so. Now, if this is your maximum underbead hardness, so and that is and so in that case accordingly you can have also the average underbead cracking sensitivity percent also. So, what is seen is that the hardness basically is increasing like this. So, if your carbon equivalent is increasing, your hardness is increasing, then bend angle basically is decreasing. So, this is your hardness, and the bending which is possible, that will be bend angle which is possible without failure. So, bend angle basically is decreasing. Similarly, the crack sensitivity also is increasing. So, as you increase increase the carbon equivalent value. So, the crack sensitivity, that is your average underbead crack sensitivity, that also goes on increasing. So, that is the effect of the carbon equivalent, and that is how it affects the the weldability of the material. So, what we were discussing that if your carbon equivalent is exceeding 0.4, in that case your underbead cracking from hydrogen basically increases. Now, the thing is that many a times the preheating requirement is mostly basically when you use the heavy sections. In that case you require the preheating, and less preheating basically will be required when you use the low hydrogen processes. So, in those cases you can have the not so much of requirement about the preheating. So, that is depending upon the low hydrogen processes or low hydrogen electrodes which you use. In that case the extent to which you have to do the preheating that may be affected. So, that is the case normally with these kind of steels, and especially when the ambient temperature is smaller. So, normally when your ambient temperature is below 10 degrees C, in those cases you need to have this precaution that you should weld it with low hydrogen electrodes. Next will be your medium carbon steels. So, as you see that when you further increase the carbon, in that case your that is defined as the medium carbon steel. So, since you increase the carbon, then normally since the hardenability is increasing, so you are expecting to have the formation of the martensite, and which is very hard and brittle phase, and you try to avoid. So, in most of the applications what you do is you normally medium carbon steels, they should be preheated prior to welding. So, for controlling that cooling rate in the weld metal and the HHR zone, what you do is normally we do the preheating. So, that preheating is somewhat essential, you can say, in the case of these medium carbon steels. Now, this preheat temperature which appropriately you are going to have, that will be depending upon many factors. So, that will be depending upon say the carbon equivalent value, then the joint thickness and what type of welding procedure you are taking. So, that is the so that way you can have the selection of appropriate preheating temperature. Now, if you have the carbon equivalent value which is coming in the range of 0.45 to 0.6, in those cases we take the preheat temperature in the range of 100 to 200 degrees C, depending upon the welding process and also the thickness, and normally the interpass temperature also will be kept same as the preheat temperature. So, that is normally the requirement in those medium carbon steel welding of these steels. Then in these cases the low hydrogen welding procedures are mandatory. You must use the low hydrogen welding procedures to avoid any kind of crack formation or undesirable microstructural products. So, normally what you do is you are going to have the low hydrogen welding processes, use of low hydrogen electrodes. Then selection of filler metal also is very important, because as the carbon content is increasing, so there may be pickup of the carbon also from the weld. So, so pickup of carbon from steel containing 0.5% carbon by dilution. So, that will result into high weld metal hardness normally. So, because that if that is picked up, then that will result into very much hardness, and if the hardness increased, then that will result into the formation of cracks, because that will not accommodate any kind of deformation which is likely to be because of the thermal gradient. So, so in those cases there is so what is done is normally when you go for the so first of all when you go for the multi-pass welds, then the thing is that you must give the low heat input in the first few layers, just to limit the dilution. We try to go for the low heat input, so that the dilution that may lead to the formation of hard phases or cracks. So, we try to have the low heat input in case of these multi pass. It is not waste, actually in case. Then stress relief post weld heat treatment is recommended highly immediately after welding, especially in the thick section. Then you also require, in the case of high joint restraint, you require basically, or wherever you have the service where you feel that it is expected to dynamic loading. So, in those cases you require to have the application of the stress relief post weld heat treatment, that should be given in those cases. And if possible, the welding joint should be heated to that stress relief temperature without immediate cooling to that ambient temperature. So, that also is one of the way by which you can avoid these formation of cracks or so. And also slow cooling to room temperature from that stress relief temperature, that is also recommended to avoid any formation of the thermal stresses. Now, when your this stress relief treatment, immediate stress relief treatment is not possible. So, so in those cases when it is not possible to have the immediate stress relief treatment, so you can maintain the above the specified preheat temperature for 5 to 7 minutes per mm of section thickness or joint thickness. So, what it does is normally that also promotes the diffusion of hydrogen so from the weld zone, and accordingly or can consequently, basically once you have that process, then it will reduce the crack formation tendency, or any undesirable process, undesirable microstructure which may result into because of the other parameters. So, that is that is what should be followed in case of medium carbon steel. Coming to the high carbon steel. So, as we discussed that the high carbon steels welding is a great challenge. So, as since the hardenability is increasing in the case of high carbon steel, so the weldability is considered to be poor, and there is great chance of the cracking in the weld metal or HAZ zone if proper precautions are not taken. So, precautions are that you will have to have the control on the thermal gradient, which is established during the welding process, heating or cooling process, and that has to be accommodated. So, normally you have you are maintaining the preheating and the interpass temperature of the order of maybe 200 to 315 degrees centigrade. So, that is the requirement when we talk about the weldability issues in the case of high carbon steel. Now, in these cases what we do is we normally go for the low hydrogen processes. So, if you go for the low hydrogen processes, in those cases your degree of preheat requirement, that is decreased. So, and what you can have also see that if you have the material thickness of less than 2 mm, so or less, then if the use of low hydrogen processes are there, in that case you can even eliminate the use of preheating. As a thumb rule, if you use these low hydrogen electrodes, in that case your preheat temperature requirement will be reduced by 45 degree to 90 degrees C lower than what you require in the normal process. So, that is normally the situation that is there in the case of the high carbon steels welding. Now, the further if you look at the high carbon steels. So, what the earlier point which was there, that if you are willing, many a times you have the you have to also consider the use of the filler material. So, so appropriate filler metal has to be selected, and normally the filler metal that dictates that there may be pickup of carbon in the weld pool. So, to reduce that pickup of carbon by the weld metal, now you must have the proper welding procedure designed, so that the dilution is is minimum. So, that is also to be taken care of. Now, when we are talking about the high carbon steel welding, so normally they should be welded in the annealed condition and then heat treated. So, that is better, that is suggested, that if you do that, then the likelihood of these crackings or undesirable effects are less. Then you have annealing is also recommended prior to the repair of broken welding parts. So, many a times welding is used for the repair of these welding parts. So, it is one of the very potential use of welding processes. So, there also if you have the high carbon steel part, in those cases you are suggested that you should go for annealing, so prior to the doing the repair work. Then post weld stress relief is recommended, particularly for if you talk about the thicker sections. So, in the thicker sections you need the post weld stress relief, so that also for that you have proper welding procedure is there. So, your post weld stress relief process is in fact very much recommended for the thick joints. So, there it is more prone to have those places, those regions are more prone to have the cracks. So, there you will have the requirement of the post weld stress relief treatment too. So, these are the issues related to the weldability in the case of carbon steels, and there we have seen the different carbon steels, low, medium and high carbon steels. So, especially once you move towards the higher carbon content, then you require these special precautions to avoid the formation of these hard phases or in weld metal and the achagar zones, and to avoid the cracking. So, we will talk about the weldability issues in other materials also in our subsequent lectures. Thank you very much.